Hello. Tonight, if you're listening to this while the room has finally gone quiet, take a moment to pause. You don't need to imagine people. You don't need to think about history. Just think about Earth, a planet that is turning, not too fast, not perfectly, and never standing still. We often think of day and night as obvious facts. The sun rises, the sun sets. One day passes like any other. But in reality, no day is ever exactly the same as another. The length of light is always changing. The length of darkness is changing too. And within those very small changes, the entire history of life has been bent and shaped. There are places on Earth where the sun does not disappear for a few hours, but for many days, many weeks, sometimes even many months. There are periods when a day does not last exactly 24 hours. And there have also been moments in the planet's history when darkness did not come from the sky, but from Earth's own atmosphere. In this video, we will not begin with myth. We will not begin with humanity. And we will not begin with a story. We will begin with geometry, with motion, with the tilt of a planet's axis, because before darkness became fear, before night became memory, it was simply a physical consequence. A consequence that Earth has repeated for billions of years, long before there was anyone there to notice. And only when we understand where night comes from can we begin to understand why it has left such a deep imprint inside the human brain itself. Adjust the volume to a comfortable level. We will begin at a place where darkness carried no meaning at all, where it was simply a natural part of a planet turning in silence. In everyday experience, day and night seem like two fixed states. The sun rises, then the sun sets. A familiar loop so routine that it is rarely questioned. We tend to think that today is in essence no different from yesterday, and that tomorrow will pass in exactly the same way. But in reality, there is no day that is ever completely identical to another. The length of light is always changing, even if only by a very small amount. The length of darkness changes as well. These changes occur continuously quietly and are almost impossible to notice in daily life. They are not errors, nor are they malfunctions in the operation of the planet. On the contrary, it is this very change that represents Earth's normal state. If we observe long enough, we begin to see that light on Earth is never stationary. It does not repeat itself in fixed blocks of time, but slowly slides forward day by day, season by season, year by year. Each morning the sun rises at a position slightly different from the day before. Each noon it reaches a maximum height that is shifted just a little. And each afternoon, the moment when light retreats does not perfectly align with the previous day. These differences are so small that clocks and calendars persuade us that today is merely a copy of yesterday. But in physical terms, Earth has never produced two identical days. Light is constantly being redistributed, little by little, across the surface of a moving planet. To understand why this happens, we do not need to begin with history. We do not need to begin with humans or culture. Those concepts appear very late in Earth's story. Instead, we must begin with something far more fundamental: geometry. Geometry in this case is not lines drawn on paper or abstract equations. It is the way an object rotates in space, the relationship between a planet's axis of rotation, its orbit, and the single source of light that governs this entire system, the sun. Earth does not rotate upright as it travels around the sun. Its axis of rotation is tilted by about 23.5 degrees relative to the plane of its orbit. This means that as Earth moves around the sun, its axis does not simply rotate with it, but maintains the same orientation in space, like a spinning top that remains tilted without correcting its posture. This tilt is not a minor detail, nor is it a decorative number in a textbook. It is the foundational condition that determines how sunlight reaches Earth. It is this tilt that causes light to fall unevenly across the planet's surface, distributed differently across time and space. When one hemisphere tilts toward the sun, light strikes it more directly. Energy is concentrated over a smaller area. The sun appears higher in the sky, and the time it remains above the horizon becomes longer. When that hemisphere tilts away, light arrives at a lower angle, spreads over a larger area, becomes weaker, and the length of the day shortens. There is no moment when Earth decides to change this. There is no event that marks a sudden transition between light states. Everything unfolds as an inevitable consequence of a planet orbiting a star with an axis that is not perpendicular to its path. From this tilt, seasons are formed, climate is shaped, and Earth's day-night rhythm is stretched and compressed at different points throughout the year. Short days and long nights are not anomalies that require emotional or symbolic explanation. They are direct outcomes of planetary geometry, operating steadily in space long before there was anyone there to notice. If Earth had no axial tilt, every location on its surface would receive nearly the same amount of light year-round. There would be no clear distinction between summer and winter. There would be no unusually long days and no extended nights. Light would be distributed almost evenly. But because the axis is tilted over the course of a year, each hemisphere alternately tilts toward the sun and then away from it. When a hemisphere tilts toward the sun, light arrives more directly, the sun's path across the sky is higher, and daylight lasts longer. When it tilts away, light arrives at a lower angle, the sun appears lower on the horizon, and daylight shortens. Nothing abrupt occurs during this process. There is no moment when Earth switches seasons. There is only geometry operating steadily, slowly, and precisely. Within this orbit around the sun, there is one point each year when a hemisphere is tilted away from the light source as much as physically possible. This moment is called the winter solstice. In the northern hemisphere, it usually occurs in late December. In the southern hemisphere, it occurs in late June. This is not a day created to mark winter, but a direct consequence of Earth's geometric position relative to the sun at a specific point in its orbit. On the winter solstice, Earth's axis reaches a configuration in which one hemisphere is oriented farther from sunlight than at any other time of the year. As a result, the sun, when observed from that hemisphere, traces a very low arc across the sky. Its maximum height at noon is the lowest it will reach all year. Light is therefore not only weaker, but spread across a larger surface area, reducing the intensity of energy received. Because the sun's apparent path is shorter, the time it spends above the horizon is reduced to its minimum. The sun rises later, sets earlier, and the interval between those two moments becomes the shortest daytime of the year for that hemisphere. This shortening produces the day with the least light, while the remaining hours stretch into the longest night when measured as a proportion between day and night. However, it is important to note that the winter solstice is not a moment when light suddenly drops or disappears. This change is the result of a very slow, continuous process. Before the solstice, each day becomes slightly shorter. After the solstice, daylight begins to lengthen again, also by a very small amount. The solstice is simply the lowest point in a smooth curve, where the trend of shrinking daylight reaches its minimum before reversing direction. From a sensory perspective, without calendars or precise timekeeping instruments, it is extremely difficult to distinguish the solstice from the days immediately before or after it. There is no obvious physical sign in the sky announcing this is the shortest day. The sun does not pause. Light does not change color. There is only a very small difference in height and duration, large enough for astronomical measurement, but too subtle for intuition alone. This shows that the winter solstice is not an event in the dramatic sense, but a geometric marker. It exists not because humans named it, but because Earth's orbit and axial tilt make its existence unavoidable. Each year, as the planet completes one revolution around the sun, the solstice appears at precisely that position, repeating with high accuracy, regardless of whatever else is happening on Earth's surface. For this reason, the shortest day of the year is not random. It is an inevitable part of the planet's structural motion, reproduced steadily over millions of years. Before humans learned to record time, before calendars or seasonal concepts existed, the winter solstice already existed as the lowest point of light, defined entirely by geometry and motion in space. Still, the winter solstice is not an event in the usual sense. It is not a break nor an easily recognizable moment. Before it, days shorten. After it, days begin to lengthen again. The transition is so smooth that without calendars or clocks, it is extremely difficult to determine which day is truly the shortest. Physically, the solstice is simply the lowest point in a very smooth curve of light over time. Although the winter solstice is a global phenomenon, its experience is not uniform across Earth's surface. Not every location feels the shortest day in the same way. The factor that determines this difference is not timing, but latitude, a location's distance from the equator. Latitude determines the angle at which sunlight strikes Earth's surface. And this angle controls not only the intensity of light, but also the length of time that light remains present each day. As latitude changes, the geometry of light changes with it, causing the same astronomical phenomenon to produce very different outcomes. Near the equator, Earth's axial tilt produces little variation in day length. Throughout the year, the sun traces a high arc across the sky, and the time it spends above the horizon changes only slightly. Day and night remain nearly balanced, each lasting around 12 hours, with variations of only tens of minutes. In these regions, the winter solstice does not bring a dramatic change in light. The shortest day of the year is only marginally shorter than others. Seasonal light changes are so subtle that they are difficult to detect without systematic observation. As a result, the experience of light near the equator is highly stable, rarely stretched or compressed by the annual cycle. As one moves farther from the equator into temperate regions, Earth's tilt becomes more pronounced in its effects. Here, seasonal differences become perceptible. In summer, the sun climbs higher and remains longer above the horizon, producing long days. In winter, the sun's path is lower and shorter, and daylight is significantly reduced. In temperate latitudes, this change is large enough to be felt intuitively. Day and night no longer remain balanced year-round. Light becomes a variable tied to time of year. Here, the winter solstice marks a clearly shorter day, where the decline of light reaches its lowest point before reversing. As one moves closer to the poles, this contrast becomes increasingly extreme. At high latitudes in winter, the sun appears very low on the horizon, if it appears at all. Its apparent path becomes so short that daylight may last only a few hours, or even less. Within the polar circles, this phenomenon reaches its limit. For part of the year, the sun's path no longer crosses the horizon. This creates periods during which the sun does not rise at all over a full 24-hour cycle, producing what is known as polar night. In some locations, this period lasts not just a single day, but many days, many weeks, and even several consecutive months. During these intervals, there is no moment when the sun rises above the horizon. Daylight, if present, exists only as extended twilight, weak in intensity, and extremely low in angle. Here, light no longer alternates in a familiar day-night rhythm, but becomes a prolonged condition dominated by darkness. This variation demonstrates that the winter solstice is not a phenomenon with uniform impact. It is a single point in Earth's orbit, but its consequences are amplified or softened by latitude. The same orbital motion can produce a nearly ordinary day at the equator, a clearly shortened day in temperate zones, and a sunless period in polar regions. For this reason, the concept of short days and long nights cannot be separated from location on the planet. Latitude not only defines where we stand, but also how light reaches that place. And it is this difference that creates Earth's highly uneven light distribution, despite having only one sun. This phenomenon does not occur because the sun disappears or because Earth stops rotating. It occurs because the sun's apparent path, shaped by Earth's axial tilt, fails to cross the horizon at those latitudes for part of the year. When we think of short days and long nights, we often imagine a sharp boundary between light and darkness. But in reality, the transition between the two is not instantaneous. After the sun sets, light continues to exist in the atmosphere in the form of twilight. This light gradually weakens as the sun sinks farther below the horizon. Only when the sun lies deep enough does the sky reach full astronomical darkness. For this reason, a long night does not necessarily mean continuous absolute darkness. At high latitudes, twilight can last for a very long time. Light may be insufficient to illuminate, yet not fully absent either. This makes the concept of night far more complex than everyday perception suggests. Viewed from outside Earth is a planet orbiting the sun with a stable axial tilt. Within this system, short days and long nights are not exceptions, but regularly repeating states. There is no year in which Earth forgets to produce a solstice. There is no cycle in which light is disrupted randomly. Before light became symbolic, before darkness acquired psychological or cultural meaning, they existed as purely physical features of a planet rotating slowly through space. In this chapter, we have not yet spoken about humanity. We have not yet spoken about history or experience. We have established only one foundation: that short days and long nights are not disruptions, nor are they catastrophes. They are direct consequences of how Earth exists. And only once this is understood can we move on to the next chapter, where darkness is no longer just a physical phenomenon, but begins to influence life on the surface of this planet. When we talk about the longest night, we often picture a continuous stretch of darkness in which light disappears completely for many hours. However, in astronomy, the concept of night is not that simple. It is not defined only by whether the sun appears above the horizon, but also by the way light continues to exist in Earth's atmosphere after the sun has already set. Therefore, before we can speak about the longest nights on Earth, one foundational point must be clarified: what night means under a scientific definition. In astronomical observation, the boundary between day and night is not a sharp cut. When the sun drops below the horizon, its light does not vanish immediately. This happens because light does not travel only in a straight line from the sun to Earth's surface. It also interacts with the atmosphere surrounding the planet. Earth's atmosphere contains multiple layers of gas dust and tiny particles capable of scattering light. When the sun is still close to the horizon, even though it is no longer visible directly, its light continues to enter the atmosphere at very shallow angles. There, the light is bent, reflected, and scattered in many different directions, including back toward Earth's surface. The result is that the sky remains bright, even though the primary light source is no longer directly present. The period during which this light remains present after the sun has set is called twilight. Twilight is not a vague phenomenon or merely a matter of perception. It is a light state that can be defined and measured precisely by the geometric position of the sun relative to the horizon. Twilight does not exist as a single uniform state. It is divided into multiple phases based on how far the sun has sunk below the horizon. Each phase corresponds to a different level of brightness in the sky and on Earth's surface. When the sun has just set, it lies only slightly below the horizon. During this phase, scattered light is still strong. The sky remains bright enough that surrounding objects can be seen clearly without artificial lighting. Details on the ground are still easy to distinguish, and the boundary between day and night is not yet truly clear. As the sun sinks deeper, the angle at which its light enters the atmosphere becomes lower. The amount of light entering the atmosphere decreases, and the scattering effect weakens as well. The sky begins to shift from bright tones toward darker shades. The brightest stars begin to appear while details on the ground become harder to recognize. At an even deeper stage, scattered light is only sufficient to illuminate the sky very faintly. The sky may appear deep blue or dark gray, and most stars can already be observed. However, background light has not disappeared completely, meaning the sky has not yet reached the ideal darkness required for precise astronomical observations. Only when the sun sinks far enough below the horizon does atmospheric scattering drop to a minimum. At that point, the sun's contribution to sky brightness becomes negligible. The sky reaches what is called full darkness in the astronomical sense, where the remaining light comes mainly from stars, distant galaxies, and other faint sources in the universe. What matters here is that twilight is not a fixed duration. Its length depends on many factors, the most important of which is latitude. Near the equator, twilight tends to pass relatively quickly. The sun descends almost vertically relative to the horizon, shortening the twilight phases. By contrast, at higher latitudes, the sun moves closer to parallel with the horizon as it sets. This causes it to sink very slowly below the horizon, extending the twilight phases. In regions very near the polar circles, twilight can last for many hours, and sometimes for the entire night, meaning the sky may never reach full astronomical darkness for a long period of time. For this reason, in astronomy, night is not simply the time after sunset. A night can be very long in the sense that the sun does not appear, yet very short in the sense of complete darkness. Conversely, in other places, night may reach deep darkness quickly, even if the period without the sun above the horizon is not especially long. This layered structure of light shows that the transition from day to night is a continuous shift with no sharp boundary. Light does not switch off. It retreats step by step, according to the physical rules of the atmosphere and the geometry of light. And only by understanding this process clearly can we speak precisely about the length of night in different astronomical contexts. Only when the sun lies far enough below the horizon does scattered sunlight in the atmosphere drop to a level that no longer significantly affects astronomical observation. That moment marks full night in the astronomical sense. Therefore, scientifically speaking, a true night does not begin immediately at sunset, but only when the final stage of twilight ends. Because of this, the length of night can be understood in different ways. It may mean the period during which the sun does not appear above the horizon, or it may mean the period during which the sky reaches complete darkness. These two definitions do not always overlap, especially at high latitudes. As one moves farther from the equator, twilight begins to last longer. At mid-latitudes, twilight may occupy a significant portion of the evening and early morning. At very high latitudes, twilight may even last throughout the entire night, so the sky never reaches full darkness, even when the sun does not appear above the horizon. This leads to an apparent paradox. there are places and times when night is very long, in the sense that the sun never rises, yet it is not fully dark in the astronomical sense. Weak light still remains spread through the atmosphere, creating a prolonged semi-dark state. To understand Earth's longest nights more clearly, attention must shift to a special phenomenon that occurs at high latitudes: polar night. Polar night is the phenomenon that occurs when the sun's apparent path does not cross the horizon for 24 hours or longer. During this period, the sun does not appear in the sky at any time of day. This can only occur within regions inside the polar circles, where Earth's axial tilt keeps the sun continuously below the horizon for part of the year. At the boundary of the polar circle, polar night may last exactly 1 day. But the farther one moves toward the pole, the longer it lasts. At very high latitudes, the sun may not appear for many weeks. And near the geographic pole, this period may last nearly half a year. Astronomically, these are the longest nights in the sense that the sun does not rise. There is no sunrise. There is no sunset in the usual sense. There is only an extended period during which the sun remains below the horizon. However, even during polar night, darkness is not always absolute. In many areas, especially near the edge of the polar circle, the sky still passes through prolonged twilight phases. Sunlight, though not direct, is still scattered through the atmosphere, producing a dimly lit sky for many hours, sometimes for the entire day. Only at very high latitudes, where the sun sinks far enough below the horizon, does the sky reach full darkness during polar night. In such places, true darkness can last for many hours each day, repeating continuously over many weeks. This distinction shows that the longest night is not a single universal concept, but depends on how night is defined. If night is defined as the time when the sun is not above the horizon, then polar night is the most extreme expression of that phenomenon. If night is defined as the time of complete astronomical darkness, then the longest night occurs only in regions very close to the poles, and it does not remain continuous for the entire period without the sun. In addition, it should be noted that the length of polar night is not exactly identical from year to year. Very small changes in Earth's orbit and axial tilt, though occurring on long timescales, can influence the start and end times of this phenomenon. However, within the timescale of human life, these changes are negligible. Polar night repeats with high regularity, tied to Earth's yearly cycle. From an astronomical point of view, Earth's longest nights are not the result of rare or abnormal events. They do not appear because of a malfunction in planetary motion, nor are they signs of imbalance. On the contrary, they are the inevitable consequence of planetary geometry and the observer's position on Earth's surface. With a stable axial tilt and an orbit maintained for millions of years, Earth recreates these long nights steadily. Each year, at specific latitudes and specific times, darkness extends according to a pattern already determined by motion in space. There is no randomness in this process. There is no year in which the nights are longer than normal in an astronomical sense, and no year in which those long nights fail to return. This high-precision repetition shows that Earth's longest nights are not exceptions, but part of the basic structure of the Earth-Sun system. They exist as extreme states of light, similar to the longest day, or the point in the year when light reaches its maximum. More importantly, these long nights do not exist in isolation. They are not blocks of darkness cut off from the rest of the light cycle. Instead, they are always connected to other light states, forming a continuous sequence of transitions from day to night, from bright to dim, and from dim back to bright. Before darkness reaches its longest extent, light has already begun to decline long in advance. The sun's path sinks lower in the sky day by day. twilight phases lengthen, occupying a larger and larger portion of the 24-hour cycle. Light does not disappear, it is compressed, spread out, and weakened in very small steps. Even when the sun does not appear above the horizon for many hours, or even many days, the sky does not shift into absolute darkness immediately. Light continues to exist as atmospheric scattering, creating prolonged twilight. These intervals may be so faint that they are difficult to sense intuitively, but physically they are still light, even under the most extreme conditions at very high latitudes during polar night. The retreat of light still follows a continuous rule. There is no moment when light switches off. It simply withdraws deeper and deeper below the horizon, leaving behind a sky that grows darker and darker, yet never changes state abruptly. This smooth transition is a direct consequence of Earth's atmosphere. Layers of gas dust and tiny particles continue to interact with light, even when the primary source has dropped out of view. As a result, the boundary between light states is always gradual, never sharp, never broken, never marked by a clear fracture. For this reason, in astronomy, darkness is not treated as an absolute absence of light, but as a state of extremely low light within a continuous spectrum. Earth's longest nights represent the lowest point of that spectrum, but they still belong to the same ongoing movement of light. Seen from this perspective, long nights are not disruptions of natural order, but evidence that the order is operating precisely. They are produced by the same laws that create day seasons and Earth's rhythm of light. And only when we understand that darkness is always bound to light, that the two do not exist separately, can we move forward to the next question, one that is no longer purely astronomical. What happens when these light states begin to affect life on Earth's surface? Therefore, when speaking of the longest nights in astronomy, we must understand that they are not merely extended periods of darkness, but special light states defined by the relationship between Earth, the Sun, and the atmosphere. They represent the limit of how light can appear on this planet's surface under certain geometric conditions. In this chapter, we have still not entered the story of life or humanity. We have only observed Earth as an astronomical object operating under stable laws. The longest nights in this sense carry no emotional or symbolic meaning. They are simply extreme states of light existing as a natural part of planetary motion. Only when we understand these states precisely can we go further to the place where darkness is no longer just a phenomenon in the sky, but begins to become a factor that directly affects life on Earth's surface. In modern life, a day is understood as a fixed unit of time, 24 hours, no more, no less. Clocks divide the day into minutes and seconds, and every human activity is arranged around the assumption that the length of a day is unchanging. However, from the perspective of geophysics and astronomy, this assumption is not entirely accurate. In reality, the length of a day on Earth is not fixed. It changes over time, changes very slowly, and changes in ways that human intuition can hardly detect. To understand why a day does not always last exactly 24 hours, we must return to the most basic physical definition of the concept. A day scientifically is the amount of time Earth needs to complete one rotation around its own axis, relative to a defined reference frame. This definition may sound simple, but the motion it describes is far more complex than a steady uniform spin. Earth's rotation is not a perfect movement. It does not occur in an absolute vacuum, nor does it exist within a completely isolated system. Earth spins in an environment continuously influenced by multiple gravitational forces and many different physical processes, both external and internal, to the planet itself. To First of all, Earth is a massive planet, but it is not uniform. Its mass is not distributed evenly from the core to the surface, nor is it distributed evenly through space. Inside Earth exist layers with different physical properties: the core, the mantle, and the crust, each with its own density, state, and dynamics. The slow but continuous movement of these masses changes the way Earth's mass is distributed over time. In addition to its internal structure, Earth is influenced by external forces. The strongest of these is the gravitational pull of the Moon. The Moon does not only create tides in the oceans, it also acts directly on Earth's entire body of material. This gravitational force slightly deforms the planet's shape, producing tidal bulges that are not fixed and that constantly shift position over time. These deformations do not remain still. They move relative to Earth's rotation axis, creating friction in the oceans and within the crust. This friction dissipates rotational energy as heat, causing Earth's rotation speed to decrease extremely slowly over time. This is a long-term process operating over millions and billions of years, but it is one of the main reasons the length of the day is not an unchanging constant. In addition to the Moon, the Sun also contributes tidal forces, though more weakly. The combined influence of these two gravitational sources means Earth never rotates in a completely free state. Instead, the planet exists in a state of dynamic balance, where its rotation rate is continuously adjusted in response to the forces acting upon it. Not only external gravitational forces, but also processes occurring on Earth's surface affect the speed of rotation. Atmospheric motion, circulating ocean currents, seasonal melting, and accumulation of ice, all of these change how mass is distributed around the rotation axis. When mass shifts farther from the axis or moves closer to it, Earth's moment of inertia changes, and its rotation rate adjusts accordingly in order to conserve angular momentum. These adjustments can make Earth rotate slightly faster or slightly slower over short periods. The change is extremely small, only at the level of milliseconds in the length of a day, but it can be measured precisely with modern instruments. The important point is that these variations are not errors or noise. They are the natural expression of a complex physical system in operation. Therefore, when we say a day is not always 24 hours, that does not mean Earth is becoming unstable. On the contrary, it shows that Earth is a dynamic system in which rotational motion always reflects the combined effects of the forces and processes acting on the planet at any given moment. From this viewpoint, the length of the day is not a fixed number frozen into nature. It is a flexible physical quantity, changing with Earth's history and with its present state. And this flexibility is why in science, the concept of a day must be understood as an average value, not an absolute standard. One of the most important factors affecting day length is tidal force. The Moon, through its gravitational pull, creates tidal bulges in Earth's oceans. These bulges do not remain directly beneath the Moon. They are dragged out of alignment because Earth rotates faster than the Moon's orbital period around Earth. This offset produces a torque, dissipating Earth's rotational energy through friction in the oceans and in Earth's crust. The result is that Earth's rotation gradually slows over time. This process is extremely slow, but continuous, and it has been operating for billions of years. Geological studies show that in the distant past, the length of a day on Earth was significantly shorter than it is today. This conclusion is not based on speculation, but on physical traces preserved in rocks and fossils, especially structures that record rhythmic repetition over time. In certain types of ancient sedimentary rock, geologists find thin layers stacked in regular patterns. These layers formed under the influence of natural cycles such as tides and the day-night cycle. By analyzing the number and thickness of these layers, scientists can infer the number of days in a year at the time the layers were formed. The results show that hundreds of millions of years ago, a year on Earth contained more days than it does today. Because the length of the year, the time Earth takes to complete one orbit around the Sun, does not change significantly over those timescales. Having more days in a year means each day must have been shorter. Estimates indicate that during many periods of Earth's history, a day lasted about 22 hours, and in even more distant periods, it was shorter still. These lines of evidence match dynamical models describing the long-term interaction between Earth and the Moon. In the past, the Moon was closer to Earth than it is today. The gravitational force between them was therefore stronger, producing larger tidal effects and dissipating Earth's rotational energy more efficiently. As a result, Earth rotated faster in the past, and that rotation rate has gradually decreased over time. However, this slowing does not occur as a simple straight line. It is not a linear process in which each passing year adds a fixed amount to the day's length. Instead, the rate of slowing changes depending on Earth's physical conditions in each phase of its history: the structure of the oceans, the shape of the continents, the depth of the seas, and the way water masses move. All influence how efficiently tidal energy is dissipated. As continents rearranged into different configurations through geological history, the way the oceans responded to tidal forcing also changed, causing Earth's slowing to speed up or slow down during different intervals. In addition, internal processes within Earth, such as mantle convection and the movement of tectonic plates, also help regulate the planet's moment of inertia. These changes can increase or decrease Earth's rotation rate over long timescales, layered on top of the overall slowing trend. Even though it is not linear, the general trend is clear: Earth is rotating more slowly. In the modern era, precise measurements show that the average length of the day increases by a very small amount over time. Each century, the day lengthens by only a few thousandths of a second. This number is far too small to affect human daily life or biological rhythms, but large enough to be recorded clearly by modern timekeeping systems. This difference becomes meaningful only when it accumulates over very long periods. Over millions of years, this gradual increase has transformed an Earth with shorter days and faster rotation into the planet we know today, with the familiar 24-hour rhythm. Over millions of years more, if the trend continues, a day on Earth will become longer still. What matters here is not the exact number for day length in each historical period, but the recognition that a day is a historical quantity. It carries the imprint of Earth's dynamical past, reflecting the long-term relationship between this planet and the bodies surrounding it. Therefore, when we look at a clock and see a day divided into 24 hours, we must understand that this is not a permanent characteristic of Earth. It is the current state of a planet that continues to change very slowly but without stopping. The concept used to describe this change is the length of day, commonly referred to as length of day, or LOD. LOD is not a fixed number. It fluctuates around an average value, reflecting small variations in Earth's rotation rate. Beyond long-term tidal effects, many other factors cause short-term fluctuations in day length. The movement of the atmosphere-ocean currents, the redistribution of ice mass, and even large earthquakes can change how mass is distributed on Earth. When mass distribution changes, the planet's moment of inertia changes as well, and the rotation rate adjusts to conserve angular momentum. These changes can make Earth rotate slightly faster or slightly slower over short intervals. As a result, there are days that are longer than the 24-hour average, and days that are shorter than the 24-hour average, even though the difference is only measured in milliseconds. Importantly, these fluctuations are not purely random. They follow physical laws reflecting the dynamic state of Earth as a complex system in which the atmosphere, the oceans, the mantle, and the core interact with one another. In that context, the idea one day equals 24 hours is a convention, not an absolute reality. It represents the average value of day length during a certain period of Earth's history, not an unchanging constant of nature. To maintain a stable timescale for science and technology, humans have built timekeeping systems based on phenomena that are far more repeatable, such as atomic oscillations. Atomic clocks allow time measurement with precision far beyond any mechanical motion of Earth. When we compare time measured by atomic clocks to time based on Earth's rotation, the difference becomes visible. Sometimes Earth rotates slightly more slowly than the standard and astronomical time falls behind atomic time. Sometimes it rotates slightly faster, bringing the two time scales closer together. To reconcile these differences, modern time systems must continuously monitor and adjust. This shows that time in the planetary sense is not a perfectly steady flow, but a dynamic quantity reflecting Earth's physical state at each moment. From this viewpoint, a day is no longer an unchanging block of time, but the result of many overlapping processes. It is influenced by the long history of interaction between Earth and the Moon, by the planet's internal structure, and by ongoing processes in the atmosphere and oceans. This also means that the length of a day in the past was not the same as it is today, and in the future it will continue to change. Earth, hundreds of millions of years from now, will have longer days than we experience today if the slowing trend continues. In addition to the concept of the shortest day in terms of the least daylight in a year, linked to the winter solstice, there exists another concept less widely known, but highly important in geophysics: the shortest day in terms of rotation time. In this case, day is not measured by light or darkness, but by the time Earth takes to complete one full rotation around its axis. Under this definition, a day can be shorter or longer than the 24-hour average, even though the difference is only measured in milliseconds. The shortest days in this sense are not directly related to Earth's position in its orbit around the Sun, nor are they tied to seasons or the solstice. Instead, they reflect tiny fluctuations in Earth's rotation speed at specific moments. During certain intervals, because of mass redistribution in the atmosphere, the oceans or Earth's mantle, the planet may rotate slightly faster than average. When that happens, the time required to complete one rotation decreases, producing the shortest days in a purely physical sense. The difference is far too small for humans to perceive, but large enough to be recorded by high-precision timekeeping instruments such as atomic clocks. This shows that the concept of the shortest day does not always carry the same meaning. A day may be the shortest in terms of daylight, yet not the shortest in terms of rotation time. Conversely, a day may rotate faster than usual while receiving an amount of daylight no different from the days around it. The simultaneous existence of these two definitions highlights an important point in science. Day is not a simple concept. It is the result of multiple processes layered together: orbital motion, axial tilt gravity, and the internal dynamics of the planet. And only by clearly separating these layers of meaning can we understand what is truly changing when we say Earth is experiencing shorter or longer days. However, on the time scale of human life, these changes occur too slowly to be sensed directly. They become clear only through precise measurement and when placed within Earth's long-term history. Therefore, when we say a day is not always 24 hours, that does not mean Earth is becoming unstable or disordered. On the contrary, it shows that Earth is a dynamic system, continuously adjusting in response to the forces acting upon it. In this chapter, we have not yet spoken about light or darkness as lived experience. We have only looked at Earth as a rotating body subject to physical forces reflecting those forces through the length of its day. The fact that a day can be longer or shorter than 24 hours is an important reminder that time units we use every day are not absolute entities of the universe. They are tools built to match a particular stage in Earth's history, and only once we understand that even time on this planet is a quantity that can change, can we move forward to the next part of the story, where variations in day and night begin to matter beyond pure physics and directly shape the survival of life on Earth. In the previous chapters, darkness was described as a physical state of light, the result of planetary geometry, axial tilt, the atmosphere, and rotation. But on Earth's surface, darkness does not exist only as an optical condition. It is an environmental factor that acts directly on life. When the length of night increases, darkness does not merely last longer in time. It changes the energy structure of the living environment. Temperatures drop more deeply and remain low for longer periods. The thermal range between day and night grows wider, making it more energetically costly to keep physiological processes stable. For life on land, this means that every cycle of extended night is accompanied by a risk of thermal imbalance and increased energy loss. Prolonged darkness also changes how organisms interact with space. As light declines, the ability to perceive the surrounding environment becomes limited. The distance one can travel safely shrinks. Behaviors that depend on vision become less effective. This affects not only the search for food, but also the ability to avoid danger and maintain territory. In that context, long night is no longer an abstract astronomical idea. It becomes a controlling environmental factor, acting simultaneously on temperature mobility, biological rhythms, and energy use strategies. This pressure does not appear in a single moment. It accumulates across night after night, forcing biological systems to adjust if they are to persist. At the biological level, light functions as a foundational signal. It does not only illuminate the environment, it also provides information about time. The light-dark cycle is used to synchronize internal physiological processes from cycles of activity and rest to metabolic regulation and the timing of essential behaviors such as foraging. When light decreases, or when darkness becomes unusually prolonged, that time signal grows faint. The system of biological regulation must rely on other signals, less stable ones, to maintain internal rhythm. This raises the risk of desynchronization among physiological processes, leading to reduced metabolic efficiency and a tested capacity for adaptation. Long nights place particular pressure on organisms whose biological rhythms are tightly anchored to the 24-hour cycle. When the light signal is no longer clear, internal cycles can drift, causing the timing of activity to no longer match the most favorable environmental conditions. This reduces energy efficiency and increases survival risk. In environments where nights lengthen seasonally, the ability to adjust biological rhythm becomes an important advantage. Biological systems that are highly flexible in adjusting activity cycles are better able to maintain balance when light becomes scarce. By contrast, less flexible systems are more vulnerable under prolonged changes in darkness. From an evolutionary perspective, long night functions as an ecological filter. It does not eliminate life immediately, but it creates conditions in which less efficient biological strategies are gradually removed. Over many generations, this pressure helps shape physiological and behavioral traits that optimize energy use under limited light conditions. For that reason, long night is not merely the absence of light. It is a complex environmental state in which time, energy, and biological information are all constrained. And it is precisely within that constraint that life is forced to change in order to continue. For terrestrial organisms, long night means lower temperatures. When the sun does not appear for extended periods, Earth's surface loses heat rapidly through radiation. Soil, rock, and air cool down, increasing the energy cost of maintaining body temperature. For species unable to regulate internal temperature, such cooling can severely limit basic activity. Even for organisms capable of maintaining stable body temperature, long nights still create pressure. Energy demands rise, while the ability to find food declines because visibility is limited and the environment becomes more dangerous. This forces organisms to adjust survival strategies, either by reducing activity or by shifting activity toward weak light periods such as twilight. In prehistoric conditions, before stable artificial light existed, darkness was nearly absolute. There was no way to extend the day. Night could not be driven away, only endured or avoided. This made the length of night a powerful selective factor. Populations living at high latitudes where winter nights are long faced greater pressure than populations near the equator. Differences in light by latitude were therefore not merely differences in experience, but differences in survival conditions. One of the clearest consequences of long night is change in biological rhythms. Most organisms on Earth possess internal biological clocks adjusted by the light-dark cycle. When that cycle is stretched or distorted, physiological processes must adapt in order to maintain balance. In environments with prolonged nights, light cues become rare and less reliable. This forces biological systems to rely more heavily on internal cues or on other environmental factors such as temperature and humidity. The ability to maintain a stable rhythm under abnormal light conditions becomes a survival advantage. Long nights also affect orientation and movement. In darkness, visibility drops sharply. Obstacles become difficult to detect. The risk of accidents increases. For species that depend heavily on vision, long night significantly reduces the safe range of activity. This leads to a divergence of survival strategies. Some species adapt by reducing nighttime activity, taking shelter, and conserving energy. Others develop the ability to function in low light using other senses, such as hearing or smell, to compensate for limited vision. In evolutionary terms, prolonged darkness acts as a filter. Individuals unable to adjust behavior, physiology, or energy strategy have lower survival probabilities. Over many generations, this results in selection for traits that better cope with long night. Long night affects not only individuals, but also the structure of entire ecosystems. Food webs shift as predators and prey adjust activity timing. Relationships between species are reorganized according to each species' capacity to exploit or avoid darkness. In environments with very long winter nights, energy scarcity becomes the central issue. With limited sunlight, biological productivity declines. Photosynthesis slows or stops reducing the energy input to the entire ecosystem. This creates a cascading chain of effects that reaches every trophic level. In such contexts, long night is not merely a period without light. It is a distinct ecological phase in which all life activities must be optimized for survival. Energy surplus becomes rare, and conservation becomes the central strategy. For prehistoric humans, long night brought challenges similar to those faced by other organisms, but with a more concentrated intensity. Without stable artificial light, darkness not only limited the range of activity, it completely altered the risk balance of the environment. When light disappears, every action takes place under conditions of limited information, and every decision carries a higher probability of error. Reduced visibility is the most direct and obvious consequence. Human vision, though advanced compared to many species, still depends strongly on light. In prolonged darkness, terrain details become difficult to distinguish, distances are misjudged, and obstacles are not recognized in time. This increases the risk of falling collision and injury events that may not be immediately fatal, but that reduce survival chances in harsh environments. In addition, responding to threats during long nights becomes slower. With limited vision, environmental information reaches the nervous system later and less completely. The time required to detect a threat increases, while the time available to respond decreases. That delay, even if small, can be enough to change outcomes in dangerous situations. In darkness, the boundary between safety and risk becomes blurred. Areas that are safe to move through in daylight become potential hazards at night. Familiar paths lose predictability, and orientation becomes less reliable. This forces prehistoric humans to shrink their range of movement during extended nights, reducing access to resources and increasing dependence on fixed shelter spaces. Errors in darkness carry greater consequences than errors in light. A wrong step, a misjudged distance, or a delayed reaction can lead to serious injury. In prehistoric conditions without medical systems or rapid recovery, such injuries could drastically reduce survival chances, not only for the individual, but also for the group that depended on them. Long nights also increase psychophysiological pressure in a biological sense. When darkness lasts longer, a state of vigilance must be maintained for longer periods. The nervous system remains active under prolonged stress, consuming energy, without producing direct benefit. Accumulated fatigue reduces the ability to make accurate decisions, creating a loop in which darkness increases risk, and risk weakens the capacity to cope with darkness. In that context, long night is not merely a period without light. It is an environment in which survival probability declines. It does not kill directly, but it gradually increases the likelihood of small incidents, and it is the accumulation of those incidents that becomes the greatest threat. From this perspective, darkness becomes a powerful selective factor. Individuals or groups that fail to adjust behavior to reduce exposure to risk during long nights face higher loss rates. By contrast, strategies that limit movement, increase predictability of living space, and reduce the need for activity in darkness provide a clear survival advantage. Therefore, for prehistoric humans, long night was not simply the absence of light. It was an environmental condition that transformed the entire evaluation of risk-forcing behavior to be reorganized around the most important goal-reducing mistakes in darkness. Under such conditions, minimizing exposure to extended darkness becomes a survival need. This does not necessarily lead to a single specific action, but it creates continuous pressure on how humans organize living space schedule activity and manage energy strategy. Importantly, long night is not an instant catastrophe. It does not kill immediately. Instead, it gradually erodes the ability to maintain biological balance. It increases energy, costs, reduces access to resources, and amplifies risk. Over the long term, these pressures are strong enough to shape behavior and survival strategies. From this viewpoint, darkness is no longer a passive state. It becomes a selective force, silent but constant. The populations that survive are not the ones for whom darkness disappears, but the ones who learn how to live within it. This chapter marks an important shift. We are no longer observing light and darkness only as physical phenomena. We begin to see them as environmental conditions capable of shaping life on Earth's surface. And when night becomes a survival pressure, the question is no longer where light comes from or how long darkness lasts. The question becomes, how did life adapt in order to survive within those long stretches of darkness? That will be the starting point for the next chapter. In the previous chapters, darkness was described as a survival pressure. It lengthens the cold limits, Information increases risk and erodes energy. For prehistoric humans, darkness was a non-negotiable condition. There was no way to change the orbit, no way to adjust the axial tilt, and no way to shorten the night through astronomical laws. But there was one single factor that allowed humans to intervene directly in the experience of darkness fire. Fire does not change the physical length of the night. It does not make the sun rise earlier or set later. But fire changes how night is experienced. By creating light heat and a local zone of safety, fire narrows darkness in an ecological and behavioral sense. Night no longer blankets the entire living space. It is cut apart, pushed back, and confined to the outer edges. Before fire was controlled, darkness was almost absolute. When natural light disappeared, the environment did not only become dim, it also lost its capacity to provide information. Space became harder to read, harder to predict, and every signal from the surroundings weakened sharply. Temperature dropped together with light turning night into a period of continuous energy loss with no mechanism for compensation. Under those conditions, prehistoric human life was tightly bound to the natural light-dark cycle. Activity was compressed into daytime. When night arrived, most behavior was forced to stop or shrink to the minimum. Not by choice, but by the physical limits of the environment. Darkness did not allow mistakes, and it offered no room for experimentation. The control of fire changed this state in a fundamental way. For the first time, humans created a source of energy that did not depend directly on the sun's position in the sky. Light and heat no longer came only from astronomical cycles. They could be maintained during periods when nature did not provide them. This did not mean humans escaped the day-night rhythm. The natural cycle still existed, and it still governed most of the environment. But the appearance of fire broke the absoluteness of darkness. Night was no longer a uniform state, covering the entire living space. It was fragmented by zones of light and warmth produced by humans. The energy from fire is local, but it is precisely this local quality that carries immense meaning. Within fire's range, environmental conditions change noticeably compared to the rest of the night. Temperature becomes more stable. Light allows a minimal level of spatial awareness. Environmental information increases even if it remains incomplete compared to daylight. The existence of such an energy source changes how humans interact with time. Night is no longer entirely passive time spent only waiting for light to return. A portion of nighttime can be used, controlled, and reorganized around the fire. More importantly, fire changes the relationship between survival and natural cycles. Before, human life had to adapt completely to the given rhythm of light and darkness. With fire, for the first time, a capacity emerged to adjust the environment to survival needs, even if only in a limited way. Night was no longer merely endured. Its impact could be softened. This turning point is not defined by how strong fire was or how far it could illuminate. It lies in this: humans created an energy source whose time of existence no longer had to match perfectly with the sun's timing. That was the first time in human history that survival time was no longer locked entirely into a single astronomical cycle. From an ecological perspective, this is a profound shift. When darkness is no longer absolute, the survival pressure imposed by long nights begins to ease. Living space can be maintained more stably. Mistakes at night can be reduced. And most importantly, the predictability of the environment increases during a period that was previously completely uncontrollable. Therefore, fire is not only a tool against cold or a way to chase away darkness. It is a marker that human life began to step out of total dependence on the natural rhythm of light. Night still existed, but it was no longer a state beyond intervention. At the physical level, fire provides two fundamental elements, heat and light. Heat slows the body's heat loss during long nights, reducing the energy cost of maintaining physiological balance. Light expands the range of visibility, even if only within a limited space. Together, these two elements create an environmental zone with more stable living conditions than the surrounding darkness. That stability is not absolute, but it is enough to change how humans organize behavior. With fire, activity does not necessarily have to end completely after the sun sets. Behaviors that were previously restricted to daylight can be extended within the bounds of artificial light. Night in this sense is shortened not in time, but in the degree of control it holds. Fire also creates a new boundary between safety and danger. In complete darkness, that boundary is blurred. With fire, space is divided into two distinct zones: the lit zone, where information and control increase, and the dark zone, where risk still dominates. The existence of such a boundary allows behavior to be reorganized in a way that reduces exposure to darkness. At the biological level, firelight does not fully replace sunlight, but it provides an additional signal. The presence of light at night changes how the body responds to prolonged darkness. The activity rest cycle is no longer abruptly severed. Instead, it can be stretched and redistributed in ways better suited to energy needs and safety. Heat from fire also alters the microclimate of living space. During long nights, as environmental temperature falls, a concentrated heat source maintains a higher local temperature, reducing the risk of hypothermia. This is especially critical in environments with prolonged winter nights, where heat loss is rapid and continuous. Maintaining a fire is not a passive act. It requires attention, fuel management, and control. But the process itself creates a new rhythm for the night. Nighttime is no longer a total void ruled by darkness. It becomes a sequence of activity intervals organized around the fire. Fire also changes how humans use space. Instead of moving through a broad darkness that is difficult to predict, activity concentrates around a fixed point. This reduces the risk of movement, increases coordination, and makes the living environment more controllable. Night, in this sense, contracts into rings of space revolving around the flame. More importantly, fire changes the relationship between humans and time in a fundamental way. Without fire, nighttime is almost an ecological blank. Light disappears, temperature falls, and the capacity for action shrinks to the minimum. Night in that state is primarily waiting time, waiting for the environment to return to a condition that allows effective activity. This waiting is not biologically passive. It consumes energy, extends vigilance, and limits the ability to allocate time to other necessary tasks. When nights are long, the total amount of time humans can use to gather resources, process materials, or maintain living space is compressed into daytime, which is already limited. The appearance of fire broke this time structure. With fire, night is no longer entirely excluded from the chain of survival activity. A portion of the night can be used even within narrow limits and at a lower intensity than daytime. Time is no longer divided absolutely into time when action is possible and time when action is impossible. This increases the total effective time humans can allocate to necessary activities, not by lengthening physical daytime, but by expanding the usable range of night. Activities that do not require long-distance movement or fine visual detail can be done within the light and warmth created by fire. Survival time, therefore, becomes more flexible. From an energy perspective, that flexibility is especially important. When activity is no longer forced entirely into daytime, the pressure to spend energy within short windows decreases. This allows work to be distributed at a more stable pace, reduces accumulated fatigue, and limits errors caused by overload in short periods. Over the long term, this shift carries evolutionary meaning. The ability to use fire does not only increase the chance of surviving each individual night, it changes the selective environment humans face. When darkness is no longer an absolute barrier, the selective pressure created by long nights begins to weaken. In environments where nights lengthen by season or latitude, the advantage of fire becomes especially clear. Populations able to control fire can maintain more stable levels of activity across unfavorable light cycles. Survival no longer depends entirely on avoiding night, but on managing it. This reduction in selective pressure does not mean darkness loses its role. Instead, it changes the criteria of survival. Rather than only those individuals who endure darkness, best surviving individuals, or groups that organize the nighttime environment more effectively gain the advantage. This opens space for behavioral and cognitive traits to develop, rather than only passive physiological traits. Across many generations, this difference accumulates into population-level advantage. Groups that control fire can maintain more stable numbers, reduce loss rates during long night periods, and exploit the environment during times that were previously unusable. Darkness shifts from an excluding factor to a condition that can be adjusted, at least partially. From an evolutionary viewpoint, this is a significant transition. Survival pressure does not vanish, but it is restructured. Fire does not erase the night, but it makes the night less decisive for existence. And precisely this change creates a new foundation in which time is no longer only endured, but becomes a resource that can be managed. Fire does not remove darkness from the world, but it fragments it. Instead of a continuous dark space, the living environment is divided into patches with different conditions. This fragmentation reduces the uniformity of survival pressure, allowing humans to choose space and timing of activity more effectively. However, it must be emphasized that fire is not a complete solution. Firelight has limited range. Heat decreases quickly with distance. Outside the direct zone of influence, darkness still exists with all its risks. This makes fire a strategic tool, not a total replacement for natural light. Precisely because of these limits, fire holds special value. It does not make humans fully independent of the day-night cycle, but it allows them to adjust their relationship with that cycle. Night is no longer a single uniform and hostile block of time. It becomes a phase that can be managed to some degree. At the behavioral level, fire enables stability in living space. That stability reduces physiological stress, reduces the need for nighttime movement, and increases environmental predictability. Together, these factors reduce the probability of mistakes in darkness, one of the greatest hazards of long nights. From this angle, fire is not only a technical invention, it is a tool that restructures the environment. By narrowing darkness within a controllable range, fire changes how night affects the lives of prehistoric humans. This chapter marks another shift in the story. If the previous chapters showed darkness as an unavoidable pressure fire, shows that the pressure can be reduced, even if it cannot be eliminated. Night does not disappear, but it no longer fully dominates. And from this capacity to shorten night, in an ecological sense, humans begin to enter a new phase, one in which the environment is not only endured, but reshaped. A single night, no matter how long, rarely shapes the entire fate of a species. The survival pressure created by darkness in a short cycle can be overcome through temporary adaptation, through luck, or through randomly favorable environmental conditions. But when long nights repeat year after year, generation after generation, darkness is no longer an event. It becomes a baseline condition of existence. In an evolutionary context, it is this repetition that becomes decisive. Long nights do not strike life like a shock, but like a durable force, quiet, persistent, and continuous. They do not immediately eliminate individuals who fail to adapt. Instead, they gradually reshape the probabilities of survival reproduction and the transmission of traits over time. When a population lives in an environment where nights are long by season or by latitude, their entire life cycle is placed within prolonged conditions of limited light. This affects not only individual behavior, but also the biological structure of the population across many generations. Traits that reduce losses in darkness tend to be retained and reinforced, while traits that are less suited gradually disappear. At the biological level, long nights create a steady pressure on circadian rhythms. When light signals are no longer regular or remain absent for too long, internal regulatory systems are forced to become more flexible. Across many generations, individuals who can maintain stable biological timing under abnormal light conditions gain an advantage. This stability is not rigidity. It is the ability to adjust without losing physiological balance. This adjustment does not happen within a single individual. It accumulates over long stretches of time. As successive generations pass through cycles of prolonged night, more suitable biological and behavioral responses are reinforced at the population level. This allows life not only to endure darkness better, but to learn over evolutionary time to anticipate it and adapt to it more effectively. During those extended dark nights, prehistoric humans did not confront darkness in an active sense. Instead, behavior tended to narrow, stabilize, and repeat. Night was not the time to expand living space. It was the time to keep familiar structures intact and reduce as much as possible variables that could not be controlled. Movement during long nights tended to be strongly limited. When light is insufficient to provide reliable information, leaving familiar space increases the probability of error. Over many generations, groups that minimized nighttime movement tended to maintain higher survival rates than groups that continued to operate broadly in darkness. As a result, the behavior of staying put at night gradually became a survival norm. Instead of moving, the time of long night was devoted to maintaining stability. This included protecting shelter space, maintaining a heat source when possible, and keeping daily structure from collapsing. These behaviors did not require strong light, but they demanded repetition and predictability traits that fit prolonged darkness. Within that safe range, low-risk activities were prioritized. Actions that did not require long-distance observation or extensive movement could be carried out at night, especially where firelight existed. Tool maintenance, material preparation, or reorganizing living space could take place within limited illumination, where risk was more controllable than in total darkness. Long nights were also a period during which biological rhythm was reaffirmed. When natural light no longer served as a clear signal, the body had to rely more heavily on internal timing. Across many generations, individuals who could maintain stable cycles of rest and wakefulness under abnormal light conditions gained an advantage. This led populations to gradually adapt in how sleep and wakefulness were distributed, according to patterns better suited to long nights. In environments where night lengthens seasonally, waiting no longer remained a passive state. It became part of survival strategy. Nighttime was used to reduce energy expenditure rather than maximize activity. Energy-saving behaviors, reducing unnecessary movement, avoiding risk, maintaining body heat, tended to be reinforced across many generations. More importantly, long nights created a context in which group coordination became more valuable than individual action. In darkness, personal information is limited, but collective information about safe space, familiar risks, shared rhythms can partially compensate. Over long time, spans populations that maintained stable group structure through the night gained a clear advantage over populations that remained scattered. These behaviors did not need to be learned in a conscious sense. they formed through repetition and selection. Ways of organizing the night that reduced risk were preserved. Ways that increased risk gradually vanished. Across many generations, darkness ceased to be a chaotic state and became a familiar condition, one in which behavior had been refined to fit. Therefore, during long, dark nights, prehistoric humans did not try to make night resemble day. They did the opposite. They organized life so that night did not need to resemble day. By narrowing activity, stabilizing space, and optimizing energy, life gradually adapted not only to the presence of darkness, but to its repetition across many generations. It is in this repetition that long night loses some of its initial threat. It does not become safe, but it becomes predictable. And in evolution, predictability can matter as much as endurance. Long nights across many generations also affected how energy was managed. In environments with limited light, surplus energy became rare. Unnecessary energy expenditure in darkness increased survival risk. Therefore, strategies of conserving energy, reducing activity during high-risk intervals, and optimizing the use of resources tended to persist. Over time, these strategies did not remain only at the level of individual behavior. They became common features of the population. The organization of time, how activity and rest were allocated, was adjusted to match long night conditions, producing a survival rhythm distinct from populations living under more stable light. Living space was also reshaped across many generations of long nights. As prolonged darkness increased, the risk of movement populations tended to concentrate activity around safe and familiar areas. Effective range of movement narrowed, but control over space increased. This reduced the probability of encountering danger in darkness in exchange for greater dependence on specific locations. That dependence, prolonged over generations, caused living space to take on clearer structure. Safe areas were used repeatedly, while high-risk zones were avoided. Darkness in this sense did not only shape time, it shaped the space in which life could exist with stability. Long nights also affected how risk was distributed within a population. Under limited light, individual mistakes could carry major consequences. Across generations, risk reduction strategies tended to be prioritized over strategies that maximized short-term gains. This changed which behaviors were selected and preserved. In this context, darkness did not directly choose the strongest or the fastest individuals. It favored traits that reduced error under conditions of limited information. Caution, predictability, and risk avoidance became survival traits of high value in environments where long nights extended across generations. Over time, these traits no longer remained temporary reactions. They became part of how a population interacted with its environment. Long nights stopped being a constantly present threat and became a familiar condition integrated into rhythm and survival strategy. At a broader evolutionary scale, nights prolonged across many generations helped produce differentiation between populations living under different light environments. Populations adapted to long night developed along a different path than populations living under stable light conditions. This difference did not necessarily appear immediately in physical form, but it became clear in the management of energy, time, and risk. The important point is that these changes do not happen in a single historical moment. There is no single time when a population becomes adapted to long night. Instead, adaptation occurs slowly, nearly imperceptible in the short term, but unmistakable when viewed across generations. In that context, long night is not an enemy to be defeated. It is a condition that must be integrated. Life does not try to eliminate darkness. It learns to exist within darkness by adjusting biological rhythm, behavior, and population structure. When night stretches across many generations, survival pressure does not act only on isolated individuals. Gradually, it shifts its focus toward how individuals exist together. In prolonged darkness, the survival of a person increasingly depends on the stability of the community to which that person belongs. Night, in this sense, becomes a quiet but persistent force of social organization. Under limited light conditions, individual behavior struggles to achieve high efficiency. Vision declines, information fragments, and mistakes carry heavy costs. By contrast, when individuals remain close share, familiar space, and repeat stable behaviors, the probability of risk decreases. Across many generations, living structures based on communal stability tend to be maintained more successfully in long night environments. Communal rhythm forms first from the need to synchronize time. When natural light no longer offers a clear signal to distinguish phases of activity, the community becomes a replacement reference. Moments of rest, moments of wakefulness, and moments of vigilance are adjusted, not only by individual biological clocks, but by the shared rhythm of the group. This synchronization reduces conflict in activity and limits out-of-phase behaviors in darkness. Over time, repeated nighttime routines, even simple ones, become a kind of survival calendar that requires no symbols and no conscious memorization. Repetition creates prediction. Prediction reduces uncertainty, and reduced uncertainty means reduced risk in an environment without light. Long nights also increase the value of continuous presence. In darkness, when an individual separates from the group, it is not only physical isolation, it is the loss of collective information. Groups that maintain close presence through the night, even with little activity, can detect environmental changes sooner and respond more steadily to unfavorable conditions. From this perspective, the community is not merely a cluster of individuals. It is a system that distributes risk. In long night, risk does not disappear, but it is shared. A mistake by one individual no longer necessarily means total failure, so long as communal structure is stable enough to absorb the shock. Communal rhythm in long night is also tied to an implicit division of roles. Not in a modern sense of formal assignment, but in repeated patterns of behavior that fit. Some individuals tend to maintain vigilance longer. Others focus more on rest and energy recovery. Across generations, this diversity helps the community maintain balance so that no single person must carry the entire survival cost of darkness. Crucially, these roles do not need to be defined or negotiated. They form through repetition and selection. Community structures in which behavioral states are distributed effectively have higher survival odds in long night environments. Long night also makes familiarity into a survival asset. Living space sound movement and the presence of familiar individuals reduce the burden on the nervous system when visual information is scarce. Over generations, communities that maintain stability of membership and space hold a clear advantage over communities that frequently change structure in darkness. This stability contributes to a rhythm of life in which night is no longer a chaotic void, but a phase with its own rules. Activity decreases, movement narrows, and focus shifts from expansion to maintenance. Communal rhythm, therefore, does not oppose darkness. It is designed to fit it. Across many generations, such rhythms become sustainable. They do not depend on ideal light conditions. They depend on repetition and predictability in low-light environments. Long night is not erased, but it is placed into order through community structure. From an evolutionary perspective, this is a critical shift. Survival pressure no longer acts only on individual physiology, but on the capacity to maintain stable communal structure in darkness. Populations that can do this survive not only single nights, but generations of prolonged night. And in that process, long night does not only shape how humans exist, it shapes how they exist together. Communal rhythm born from extended darkness becomes one of the quietest foundations for later social development, not because night offers something new, but because it forces life to reorganize itself in order to continue. When fire appears and becomes controlled as analyzed in the previous chapter, the pressure of long night begins to be softened. But what matters is this fire does not appear into an evolutionary vacuum. It is received by populations that have already lived through many generations alongside darkness. The earlier adaptation strategies become the foundation for using this new tool effectively. Therefore, the impact of fire is not only in illumination or warmth. It lies in how fire interacts with behavioral and biological structures formed across generations of long night. Populations that have learned to organize time and space in darkness are better able to integrate fire into survival life effectively. From this view, long night across generations is not only pressure, it is also preparation. It shapes the traits required for environmental intervention, like fire, to become a true evolutionary advantage. Without thousands of generations living in darkness, the impact of fire might have been very different. This chapter closes with an important recognition. Life does not adapt to rare events, but to repeated conditions. Long night, when extended across generations, becomes one of the most powerful repeated conditions prehistoric humans ever faced. And precisely in that repetition, the foundations for humanity's next steps were laid not through blazing light, but through patience accumulated in darkness. In the evolutionary history of humankind, Homo sapiens was not the only human species to exist. Within the same geological span, many other human species lived, adapted, and disappeared. Some may have had greater physical strength. Some had brains no smaller. Some survived for hundreds of thousands of years in harsh environments. Yet in the end, only one species remains to the present. The question of why Homo sapiens survived is often framed as a question of intelligence technology or biological superiority. These answers are attractive because they are simple and easy to repeat. The smarter, more creative, or more advanced species replace the others. But when that question is placed within the context of the previous chapters, where long night's darkness and survival pressure stretch across many generations, such an explanation becomes insufficient. In a world dominated by instability, absolute advantage rarely lasts long. Being stronger under one set of conditions can become a disadvantage when those conditions disappear. Being more intelligent in one particular way can become useless when the environment no longer suits that kind of intelligence. Evolutionary history shows that strategies optimized for a stable state often fail when that state no longer repeats. Homo sapiens did not survive because they excelled in a single factor. They survived because they were the least dependent on environmental stability. Their fitness did not lie in doing one thing best, but in the capacity not to collapse when conditions changed. The world in which Homo sapiens evolved was not a long-lasting balanced environment. It was a world in constant fluctuation. Climates shifted on long and short cycles. Ice sheets expanded and retreated. Sea levels rose and fell. Vegetation zones moved, and light cycles changed with latitude and season. Long nights were not an exception, they were part of that structure. In such a world, the ability to endure one fixed condition, no matter how well, does not guarantee long-term survival. A species perfectly adapted to deep cold may struggle when the environment warms. A species optimized for stable light may be disadvantaged when the light-dark cycle becomes irregular. Survival is no longer the question of who is best, but who is least vulnerable when everything changes. At this point, the advantage of Homo sapiens becomes clearer. They did not evolve to be perfect in one single environment. Instead, They developed a set of traits that enabled continuous adjustment of behavior, adjustment of social organization, adjustment of energy use, and adjustment of rhythm of life according to conditions of light and climate. This capacity to adjust is especially important in the context of long nights. When light is no longer a stable signal, survival strategies that depend entirely on a fixed day-night rhythm become fragile. Homo sapiens did not need the night to be short or long, according to a standard. They needed the night to be predictable enough to use, and when it was not predictable, they had the ability to reorganize behavior in order to reduce risk. An unstable world also makes mistakes more dangerous. When environments change quickly, decisions that were correct in the past can become errors in the present. Homo sapiens could not eliminate error, but they developed structures that reduced the consequences of error-sharing risk within the community, dispersing activities and refusing to place survival entirely in a single strategy. Across many generations, it is this capacity, not strength, not pure intelligence, that was selected for. Populations that could adjust their rhythms when nights grew longer, when seasons shifted, when resources became scarce, had a higher probability of persistence than populations dependent on prolonged stability. From this perspective, Homo sapiens did not survive because they rose above nature, but because they did not fight nature's instability. They accepted that the world was not balanced, and they organized life so that it could continue, even if balance was never achieved. This is a form of adaptation that draws little attention, yet has profound effects. It does not create obvious morphological markers in the short term, but it changes the way selection pressure operates. Instead of selecting for traits optimized for a fixed environment, evolution gradually favors survival systems that can bend without breaking. In the context of long nights repeated across generations, this bending is decisive. Darkness does not need to be defeated. It needs to be accompanied, integrated into rhythm of life, into community, and into collective memory. Homo sapiens survived because they developed this capacity earlier and more consistently than other human species. Therefore, the answer to the question, why did Homo sapiens survive, is not found in an explosive moment of intellect, nor in a single invention. It is found in tens of thousands of years lived amid instability, where long nights, climate volatility, and uncertainty were not eliminated, but became part of the way of existing. At the biological level, Homo sapiens did not possess extreme traits. Their bodies were not optimized for deep cold, as some other species were, nor specialized for harsh heat. Yet, it is precisely this lack of specialization that produced flexibility. When the environment changed, when nights grew longer, when cold seasons extended, when light became difficult to predict, this flexibility allowed adjustment without breaking physiological balance. In the context of long nights, this matters in a particular way. Prolonged darkness does not merely test the capacity to endure cold or hunger. It tests the ability to organize time and energy. Homo sapiens were not the first human species to face darkness, but they were the species that developed multi-layered strategies to reduce its impact. One of the key factors was the ability to allocate behavior according to conditions rather than according to a fixed rhythm. In environments with long nights, Homo sapiens activity could contract, spread out, or shift without collapsing the structure of survival. When necessary, they could reduce activity. When conditions permitted, they could expand. This elasticity helped maintain stability through unfavorable cycles. The ability to control fire, as analyzed, played an important role, but it was not the only factor. Fire is effective only when integrated into an existing way of organizing life. Homo sapiens did not merely know how to make fire. They knew how to place fire in the right position within communal rhythm as the center of nighttime space as a stabilizing point of heat, and light as a time marker within darkness. Yet fire cannot explain everything. What makes Homo sapiens different lies in how they live together under uncertainty. Across long nights repeated through generations, community is not only where resources are shared, it is where risk is shared. When darkness increases the probability of error, distributing risk across many individuals reduces the probability of total collapse. Maintaining a stable community through long nights requires a high level of social flexibility. Homo sapiens could maintain groups large enough to share information, yet flexible enough not to become rigid. Social structures did not need to be fixed. They could expand, contract, or reorganize depending on light season and environment. Another crucial factor is the ability to transmit information across generations. In the context of long nights repeating, requiring each generation to relearn how to survive in darkness is a serious disadvantage. Each cycle of relearning consumes energy and time, and carries the risk of error costs that an unstable environment does not allow to repeat endlessly. Homo sapiens survived not because they avoided learning, but because they reduced the cost of learning by passing experience forward. This transmission did not occur as abstract knowledge or formalized systems. It did not require complex language nor symbols. For most of evolutionary history, it occurred through repeated behavior within stable space and time. Children grew up watching how the community responded to darkness, how nighttime was used, and how risk was avoided. These observations were absorbed gradually without direct instruction. In long night environments, the most important knowledge is not what to do, but when not to do anything, when to stop moving, when to wait, when to preserve existing living structure instead of searching for new opportunity. If those decisions are wrong, consequences may not appear immediately, but they increase the probability of long-term loss. Across many generations, rhythms of life that reduce risk in darkness are preserved through communal habit. No one needs to explain why things must be done that way. Behavioral stability itself becomes the mechanism that stores information. When a rhythm of living repeats long enough, it becomes normal life, and behaviors that deviate from it become rare. In this context, the community functions as a distributed memory. No single individual needs to hold the full body of experience. Instead, memory of how to exist in the night is divided and stored within shared structure, in how space is organized in the timing, when activity drops in how energy is conserved. When a new individual grows up, they do not need to rediscover darkness from the beginning. They enter an environment already adjusted. This accumulation changes how darkness is experienced. A long night, if it is the first time, may cause chaos. But when it repeats across generations, it becomes an event with precedent. Not every detail can be predicted, but a response framework already exists. This greatly reduces uncertainty, one of the most intense survival pressures. Crucially, this knowledge is not lost when an individual dies. It remains in communal structure as long as that structure survives. This creates a major evolutionary advantage. The population does not need to restart from zero every time conditions become unfavorable. They inherit a set of responses tested by time. In environments where long nights recur cyclically, this predictability becomes especially important. When darkness returns, it is no longer a novel event. It is a familiar phase with accepted limits. Life rhythm does not break. It shifts into another mode, slower, more conserving, and more stable. From an evolutionary standpoint, this is an effective but largely invisible form of adaptation. It leaves no clear fossil trace. It does not produce obvious morphological differences, but it changes survival probability across generations. Populations that can preserve and transmit ways of living in darkness maintain continuity, while populations that must repeatedly reinvent survival strategy face higher risk. Therefore, darkness is not only an environmental condition, it is a test of collective memory. Homo sapiens survived not only because they adapted quickly, but because they did not need to adapt from the beginning each time. Accumulated memory held in behavior, habit, and rhythm allowed them to enter each long night with fewer surprises than even their own more distant ancestors. Over time, this produces a significant shift. Darkness is no longer a new trial each generation, but a familiar part of the world. And in evolution, familiarity can matter as much as strength. This creates an important evolutionary advantage: reduced surprise. In survival, surprise is often more dangerous than harshness itself. A long night can be endured if it is anticipated. An unfavorable light cycle can be passed through if it is familiar. Homo sapiens survived not because they eliminated uncertainty, but because they made uncertainty familiar. Compared with other human species, Homo sapiens tended to rely less on a single strategy. When one mode of survival became less effective due to environmental change, they could shift to another mode without breaking the entire living structure. This diversity of behavior is a major advantage in a world of long nights and climate volatility. Importantly, these traits did not appear suddenly. They are the result of tens of thousands of years living in environments where light was unstable, where night extended across generations. Homo sapiens did not defeat darkness. They integrated darkness into their way of existing. From an evolutionary perspective, this is a sustainable strategy. Instead of optimizing for one specific condition, Homo sapiens optimized for adjustability. When the environment changed, adjustment did not need to restart from the beginning. It rested on foundations accumulated through many generations. Thus, the answer to the question, why did Homo sapiens survive, is not found in a single invention, nor in a single biological trait. It is found in how the entire survival system was organized, from physiology to behavior to community to the way time and darkness were managed. In the world of long nights, life does not favor the strongest, but favors those who make the fewest mistakes under conditions of limited information. Homo sapiens survived because they learned how to reduce mistakes through community, through flexibility, through accumulated memory, and through accepting that darkness is an inseparable part of the world they inhabited. This chapter does not end with a claim of superiority. It ends with a quieter recognition. Homo sapiens exist today not because they rose above nature, but because they learned to live within the limits nature imposed, among which long nights were one of the harshest limits of all. For most of evolutionary history, night existed as a condition rather than a concept. It arrived, it lasted, and it withdrew without needing to be named, without needing to be recorded. For species that depended entirely on natural light, night was merely the empty interval between two periods of activity. But for Homo sapiens, as darkness stretched across generations and began to be managed through fire community and collective memory, night gradually shifted in its status. Night was no longer only something to be endured. It became part of the order of time. The act of counting nights did not arise as a mathematical act or as a sudden intellectual invention. It emerged as a consequence of the need to predict. When darkness repeats in cycles by season, by latitude, by the movement of the sky, survival no longer depends solely on immediate reaction, but on recognizing repetition. And to recognize repetition, humans must begin to distinguish one night from another. At first, that distinction is extremely crude. It is not a number nor a unit of measurement, but a sense of duration formed through repeated experience. Night is felt by the body before it is recognized by conscious thought. The cold deepens, fatigue accumulates, breathing slows, alertness declines, then rises again. All of these signals combine to produce an overall impression. This night is shorter or longer than the nights before it. Through repeated cycles, these small differences become familiar. Some nights end before the body slips toward exhaustion. Some nights last so long that all activity must be reduced to an absolute minimum. These experiences are not remembered as individual events, but as patterns. Night is no longer an undefined darkness. It becomes a sequence of recognizable states. In that context, collective memory does not preserve which numbered night it is, but what kind of night it is. A safe night or a risky night. A night in which activity can be sustained, or a night that forces waiting. These classifications, however vague, are enough to guide behavior. They create time markers that require no symbols yet still regulate life. When fire allows humans to maintain light at night, this structure becomes even clearer. Night is no longer a single continuous block of darkness from sunset to sunrise. It begins to be subdivided by the state of the fire. Light is no longer merely something that is present or absent, but a quantity that changes over time. There are stretches when the fire is still strong, when light is sufficient to preserve spatial awareness and close-range interaction. There are stretches when the fire weakens, when light is only enough to perceive movement very nearby. And there are stretches when the fire is nearly out, the warmth drops, and darkness begins to press into the living space. Each stretch carries a different survival condition. These transitions do not occur abruptly. It is precisely this slow transition that creates the inner rhythm of the night. Night does not only begin and end, something unfolds inside it. Body and behavior gradually adapt to that unfolding. Activity declines as light declines. Vigilance rises as warmth falls. Rest deepens as movement becomes constrained. Across generations, these rhythms are integrated into how the community exists. No one needs to name each phase of the night. Repetition alone, sustained long enough, ensures that every new individual grows into a structure that already exists. Night does not need to be explained. It is lived through in a familiar sequence. Crucially, this structure of time does not depend on precise astronomy. It does not require knowing how many degrees the sun lies below the horizon. It relies on more intimate signals, firelight temperature, bodily fatigue, and shifts in the behavior of those nearby. These signals are stable enough to create a sense of order even when the outside environment is deeply uncertain. When night has an inner rhythm, humans are no longer entirely swept away by darkness. They do not calculate the night, but they can locate themselves within it earlier or later, near the beginning, or closer to the end, almost finished, or still long ahead. This ability to locate oneself reduces survival stress because it provides a certain degree of predictability. Over long spans, the inner rhythm of night becomes a foundation for further advances in time awareness. But at this stage, what matters is not precise counting. It is not becoming lost in time. Night is no longer an infinite darkness. It has structure sequence and recognizable transition points. And it is precisely when night has structure that life can cling to that structure in order to persist, not by illuminating all darkness, but by dividing darkness into portions that can be endured and anticipated. The emergence of this rhythm is a necessary condition for counting nights, not counting with numbers, but counting through expectation. When a community knows that after a certain number of nights, light conditions will change, behavior begins to adjust before the change occurs. This preparation shows that night is no longer experienced only in the present, but placed within a sequence of time. At this stage, night becomes a unit of memory, not memory of a specific event, but memory of a cycle. Nights like this have happened before, and therefore nights like this will happen again. That recognition reduces uncertainty, one of the most dangerous elements in survival. When humans begin to distinguish nights as a sequence, they do not only recognize that night repeats, they begin to recognize that not all nights are the same in function. The difference is not located in the sky or in the positions of celestial bodies, but in the effects each night has on the body, on behavior, and on the ability to endure. Some nights are experienced as nights of waiting. On these nights, behavior tends to contract quickly, activity drops early, and energy is conserved more strongly. These are nights when the community settles into stillness, no expansion, no experimentation, no pursuit of the new. Waiting in this context is not passive. It is a survival choice when conditions are unfavorable. Other nights are transitional, not fully still and not expanding either. These nights often accompany an approaching change temperature, shifting light, increasing or decreasing, or the rhythm of life preparing to enter another mode. Behavior during transitional nights tends to be cautious yet flexible, not fully stopped, but not fully expanded. And there are nights that function as signals, not signals through clear visual signs, but through familiar sensation, a certain kind of cold, a recognizable level of fatigue, the way firelight weakens or lasts. Nights like these suggest that a new phase is approaching. Light will change, resources will shift, or risk will rise in the nights ahead. What matters is that these distinctions do not need to be named. They require no words, no symbols. They exist in how behavior is adjusted, when activity drops earlier, when storage is prioritized over searching, when risk is avoided more strongly than in prior nights. Behavior becomes the language of time. Across generations, these functional differences are reinforced through repetition. Children do not need to be taught this is a waiting night or this is a transitional night. They observe how adults behave, and through that, they learn the rhythm of time. The learning is passive yet durable. This process does not require advanced abstract thinking. It does not require counting, measuring, or formal generalization. It relies on pattern recognition, a cognitive capacity that has existed very early in the evolution of animals with developed nervous systems, recognizing that a familiar state has returned, recognizing that a sequence is repeating, and adjusting behavior accordingly. Homo sapiens did not invent time in the conceptual sense. They did not create time as an independent entity. Instead, they developed the capacity to live within structured time, a time divided into phases with different functional meanings, even if those phases are never named or counted. This capacity is especially important in a world of long nights. When light is unstable, when environments change in cycles that are difficult to predict, pattern recognition reduces risk. Instead of responding to each night as a new event, humans respond to a sequence of nights as a familiar process. At this point, time is no longer merely something that passes. It becomes a source of information. Knowing which phase of a sequence of nights one is in helps the community adjust activity levels, allocate energy, and prepare for what is coming. It need not be perfectly accurate, only accurate enough to avoid major mistakes. Across generations, this way of living creates a subtle but important difference between Homo sapiens and many other species. Not because they foresee a distant future, but because they are not completely trapped in the present. They live in a present with length stretched by memory and expectation. And within that present with length-long night is no longer a string of separate, disconnected darkness. It becomes an ordered process. No explanation is needed. No symbols are needed. Only repetition sustained long enough for behavior to learn how to move with time. When night is recognized as a sequence, the difference between present and future begins to blur. Behavior does not respond only to conditions happening now, but to conditions that are about to happen. This is an important shift. Survival is no longer only reaction. It becomes preparation. Across generations, counting nights in this sense becomes part of communal rhythm. Children grow up in an environment where night is not a random void, but an ordered phase. They do not need to be taught what night is. They learn how to live within night through the repetition of behavior around them. At this stage, the boundary between biology and culture begins to blur. Counting nights is not entirely in the body and not entirely in conscious thought. It exists in the way the community organizes time through habit, through stable rhythm. Night becomes part of social structure, even before there are clear rituals or symbols, as the ability to count nights is reinforced through sensation and anticipation. Rather than measurement, humans begin to place night within larger sequences. Night is no longer compared only to the night before it. It is set beside other repeating signs in the surrounding world. Among these, the clearest and most easily recognized is the moon. The moon does not need to be understood as a celestial body. It does not need to be explained through orbit or illumination phases. The only thing required is its steady change. The moon grows larger and then smaller, brighter, and then dimmer. And these changes unfold slowly enough for humans to notice, yet regularly enough to be anticipated. Across generations, lunar changes begin to be linked with changes in the experience of night. Nights with a bright moon differ from nights with a dim moon. Visibility differs. Risk differs. Activity rhythms differ. This association requires no explanation. It forms through repeated experience. When the moon is like this, the night will be like that. From the moon, the association extends to slower cycles, seasons. When certain sequences of nights consistently accompany colder conditions, drier conditions, or shifts in resources, humans begin to recognize that night does not exist apart from the environment. It is part of a larger motion where light, temperature, and life change together on a long rhythm. At this stage, prediction does not need precision. It is not necessary to know how many nights remain until the season changes. It is enough to know that a certain kind of night usually does not last forever, and that after a sequence of nights like this, conditions will become different. That recognition is far more powerful than any specific number. It reduces the sense of darkness as infinite. The link between night and environmental cycles also does not exist in the mind of a single individual alone. It is maintained in communal rhythm. When a community adjusts behavior together in familiar sequences of nights, reducing activity, prioritizing storage, avoiding risk, this association becomes stable and difficult to break. Crucially, these cycles do not need names. There is no need for the concept of month or season in the modern sense. They exist as repeating behavioral patterns. When the pattern returns, behavior returns. Time in this sense is preserved not in symbols, but in ways of living. When night is placed within lunar and seasonal sequences, human predictability increases by another step. Not the prediction of every detail, but the prediction of direction. Nights will grow longer or shorter. Risk will rise or fall. Resources will become scarcer or more abundant. These predictions are sufficient to adjust survival strategy at an overall level. Across generations, this linkage makes the world more ordered, even if not more stable. Uncertainty does not disappear, but it is framed. When a difficult night arrives, it is no longer felt as an isolated event, but as part of a sequence that has happened before. This profoundly changes how humans exist in darkness. Night is no longer a period cut off from the stream of life. It becomes a segment within a larger loop. And when darkness is placed within a loop, it no longer overwhelms completely. It has a position. It has a before. It has an after. At this stage, humans do not yet understand the world scientifically, but they have begun to live in a world with rhythm, where night, moon, and season connect tightly enough to generate expectation. And in survival, expectation, however vague, is a tool as powerful as any technology. It is here that night begins to exceed the boundary of pure survival. It becomes an object of attention, not because it is mysterious or sacred, but because it carries information. Night does not only hide the world, it signals shifts that are about to occur within that world. Counting nights, therefore, is not an act separated from survival. It is the natural extension of the need to reduce risk. When environments are unstable, recognizing cycles helps humans avoid wrong decisions at sensitive moments. Counting nights is how humans anchor themselves in time when space and light become difficult to trust. Over long spans, counting nights lays the groundwork for more complex time concepts. But at this stage, what matters is not quantity, it is order. This night comes after that night. A sequence can be awaited. And when something can be awaited, humans are no longer entirely swept along by uncertainty. In evolution, the ability to wait in a structured way is a major advantage. It allows energy to be conserved, unnecessary risk to be avoided, and preparation to occur for what is coming. Homo sapiens were not the first species to recognize the repetition of night, but they were the species that developed the ability to organize life around that repetition. This chapter does not end with the birth of calendars, symbols, or numbers. It ends earlier, but deeper. When humans began to count nights ecologically and behaviorally, they crossed an important boundary. Night was no longer only time that vanished. It became time that could be placed into order. And when time is placed into order, life is no longer completely trapped in the present. It begins to exist within a longer flow where past, present, and future are connected by repeating nights. Not the shortest day ever measured, not the longest night ever recorded, not a rare moment in Earth's motion, but something far more familiar, the feeling of light slowly retreating and you having to wait without knowing exactly when it will return. If you're listening to this at night, try noticing something outside your window. How dark is it right now? Is it a deep darkness? Or is it softened by the city lights? Tell me in the comments, where are you listening from? What time is it for you right now? Because the interesting thing is, at the moment you're listening, Earth is still turning. And somewhere far away, the sun has just risen. For most of our history, humans had no clocks, no calendars, no precise concept of tomorrow. They had only one very simple question, repeated again and again through every long night. Will the sun come back? And that question kept them together. It made them build fires. It made them tell stories when there was nothing else to do except wait for the light. Today, we rarely have to wait for the sun to feel safe, but our brains were still shaped in nights that were longer, colder, and far more silent. Maybe that's why you're listening to a slow voice in this darkness. Not to learn something new, but to feel that you're not alone. If this story slows you down, even a little, if it makes you look at darkness not as an empty space, but as a very ancient part of what it means to be human, leave a comment. Just one line is enough. And if you want, in the next videos, we can go even deeper. The long nights of the Ice Age, the sleep of prehistoric people, or why humans have always told stories before bed. Tell me where you want to continue in this darkness. And now, if it's already late where you are, let this voice grow quieter. Earth is still turning, darkness is still moving, and somewhere, the light has already begun to return.